Okay, please turn to page 473, problem 9.7. And now we are given a case of conducting rod that move with a constant velocity of 3 millimeter second per second in positive z direction as shown here. And then this rod has a length of 40 cm and it is placed nearby to the very long straight wire carrying current of 15 ampere with distance of 20 cm. Okay, now we are going to calculate the EMF induced in the rod here, and then we are going to state which end is at higher potential. Okay, so now since you are dealing with movement of rod, so for sure this is a case of motional plus the I is not time varying, so it's a case of motional EMF. So let's recall our third general equations under motional case. So the first one we have here, the EMF negative d flux over dt, first equation. And second one we have here EMF, since the I is not time varying, so for sure the B also is not time varying, so you can simply have this full derivative and negative d over dt integrations b dot ds, second equations. And also, as we derived last time, we also have the third equation of motional EMF equal to EMF here, close integrations u cross b dot dl. That's going to be our third equations of motional EMF. Alright guys, so now since we are dealing with a very long straight wire here, so we can simply use the general equations of H field that due to very long wire as shown here. So the B field is equal to mu naught H, and H can be found using the general expressions of H field that due to infinitely long line current given as mu naught I 2 pi r phi directions, right? This one is case of the I flowing in positive z directions. Alright, that's our general expressions of B field, and for sure it has unit of Tesla because B field. Now let's substitute this B into the standard EMF equation for the motional case. So now before that, if we draw the diagram from top view, you can see that, right? So let's draw together from top view. So that's going to be our long line current, is it, with I here, and then there is a nearby road that move along positive z directions, and it has a fixed distance from the line current which is equal to A, and also it has a length of B as shown above, right? This one from top view. So now let's say we are going to find the B field at any point along the road. Okay guys, so let's say we choose this particular point or sample along anywhere. So now we can simply find the B field that actually penetrate or passing through this sample or point of interest. So let's draw the B field. So since the current here flowing in positive z directions, so by right the H or B field must have directions in positive phi directions or counterclockwise directions. So let's draw together the field that passing through that point of interest, right? Let's say that's our B field or H field. So that's our H field direction counterclockwise. Okay guys, so you can see from here guys, at this particular point of interest or at this particular sample that taken along the road, the B field actually has directions in negative x directions, right? For the tangential component of B field at this particular point of interest, the B field will have in that directions. Let's say B naught, any magnitude, in that directions. Okay, so that's our B field that actually passing through at this tangential point of interest. Okay, so now we also know that guys, the R here is actually the distance that perpendicularly measured from the line current to the point of interest. So my question, does the sample here has any specific distance from the line current? No, it doesn't have, because the sample can be taken anywhere along the road, which from this point until that point. Or in other words, we cannot simply put any specific distance at this R. So we have to use a variable. Okay, so since the road is being placed along the y axis, so we can simply have the variable of distance given as y. Okay, so that's going to be our distance in a variable. Okay, you must use a variable in y because the distance is not fixed, right? Can be anywhere between this edge until this edge. Okay, so in other way we can simply change guys this r into y, and then since we know that guys the b at this particular point will have in negative x direction, you can simply also change this direction phi into negative x directions. Okay, now we can use this whole expression of B into this EMF equations. So let's do together. So now we have here the EMF integrations, the U here guys, U naught in Z directions, right? And then cross the B as we obtained earlier here, just put everything, mu naught I negative x over 2 pi y, and now the L term. So since the road now is placed along the y axis, right, that's our y, it's from here, that's our axis, and then that's going to be our z. Okay guys, so we can simply use here dot y dy. So let's perform the cross product between z and also minus x. Okay, so by guys, z cross x, we're gonna have y, so now we have negatives, so we're gonna have here minus y directions. Okay, now turn to the limit of the integrations. So how do we determine the limit? So it's simple, we can simply know the limit by look at to the current flow. Okay, and then the current flow can be determined by the cross product between u and b. Okay, now let's use your right hand. Now the u actually pointing in positive z directions, and cross the b actually pointing in negative x directions. And now you can see your thumb fingers showing the current flow, which actually flowing in negative y directions. So that is going to be our I directions, which is from B to A in negative y directions. So that's going to be our current directions. So now guys, from the diagram, we know that the limit from here actually from B to A, the B here actually measured from line current A plus B until A, which is A, right? Now we have here from B, which is A plus B, until A, which is only A. That's only our limit. Okay, now let's integrate over Y. So now we're gonna have length term, isn't it? So now we have here mu naught I naught, mu naught U naught, sorry, I over 2 pi. Now I'm going to remove this negative. I just rearrange the limit. Now I have here A plus B over A volts. So if you substitute all the value of A, B, U naught, and also the I, you're going to have the value of EMF mu naught is 13 for the U naught, and then the I is equal to 15 over 2 pi ln A plus B equal to 60 cm over 20 cm, which will give us the value of 9.888 microvolts. Okay guys, all right, look at to the I directions. Now the current flows from B to A, so we can simply know that this terminal or this edge actually at higher potential. Meanwhile, at this edge or this terminal is actually at lower potential. Okay guys, all right, so I hope you learned something, and please redo, and all the best for your revisions. Thank you.